This is what we call a position velocity acceleration problem, and we will tackle it much more in depth in Unit 3. But for now, I'll just start with the y equation is the position of a particle that's moving up and down a vertical line, and t is time, and time equals 0. So the first thing they want us to do is find the velocity function, and that is just going to be y prime. So let me do that first. I'll do it up here. Y prime by the power rule will be 3t squared minus 12. Then it wants the acceleration function, which is y double prime, which is just going to be 6t. Then they ask, when is the particle moving up and when is it moving down? Well, the particle moves up when y prime is greater than 0 and moves down when y prime is less than 0. So what we want to do for part B is set the derivative equal to 0 and find the zeros. So let's see, we'll have 3t squared equals 12, t squared equals 4, and then t would be plus or minus 2, but since t is only positive, t is 2. So the question is, between 0 and 2, we know that at t equals 2, the particle is changing direction. So the question is, between 0 and 2, is the particle traveling up or down? Well, if I plug in 0 into my derivative, I'm going to get out a negative number. So my downward motion is going to start where time equals 0. And then if I plug in some number like 1, I get that the motion is still downward. So I think we're going to find that at time equals 2, the particle changes directions. So the particle goes downward from 0 to 2. Then, if you notice that this derivative equation is a parabola, so its shape will look like this. So if this is time equals 2 right here, then after time equals 2, the derivative function will be increasing. Let's see, that wouldn't be time equals 2. Let's see if I can do a better job at this, graphing this guy. We have zeros at -2 and 2. And we have a y-intercept at -12. So let's really graph this. So we notice at time equals 2, the particle changed direction because the derivative changed signs, and the velocity of the particle is positive after the time when time equals 2. So the particle travels upward from 2 on to time equals infinity, because that is where y prime is greater than 0. And then part C, find the distance that the particle travels from 0 to 3. Well, basically what you want to do is find the position of the particle at y equals 0, or at time equals 0, time equals 2, and time equals 3. So let's start with that. The position of the particle is right here. The position at time equals 0 is 3. The position at 2 is going to be 8 minus 24 plus 3, which is 19. And at time equals 3, the position is 27 minus 36 plus 3, which is -6. And I just realized I made a mistake. At y equals 2, I have 8 minus 24, which is -16, plus 3, which is -13. And then I'm okay with 27 minus 36 plus 3 being -6. So you can see the particle moved from 3 downward to -13. That was, let me see if I can clarify, this was the down motion. It went down from 3 to -13, so it went down by 16. And then the up motion went from -13 to -6, so it went up by 7. So the distance traveled by this particle is 23 in total. And they did not give us units, so we just say 23. So basically, just to confirm what I did here, I chose these three values. The endpoints of the interval were 0 and 3, and I chose time equals 2 because that's where we figured out that the derivative changed sign, so the particle changed direction. So we want to measure how far the particle went down, and then how far the particle went up to get the full distance traveled.